Okay, 1.6 piecewise functions. So what is a piecewise function? These are also called hybrid functions. I'm going to be calling them piecewise functions, and they're defined by different formulas for different intervals, aka domains, okay, of the independent variable. Standard notation is given in the following format. So what happens is we have f at x, but instead of having f at x equals and then one formula, we now actually have it equaling to three different formulas. Okay, you could have three lines in here. You could have one with just two different formulas. You could have one with five. Okay, so when I think of the word piecewise, I think of the word piece. Okay, we're breaking it down into little pieces. Okay, and then so however many formulas there are in our piecewise function, they're going to have the formula. Say it's a quadratic, and then it's going to say if, or it's just going to state a domain. Okay, the domain in which this formula is defined. And then the second formula, say it's like an absolute value part of the graph, and then that's going to be defined on a different part of the domain. And then formula 3, say it's like a reciprocal function. I'm just making this up, but again, it's just gonna list all the formulas and then list all the domains in which that formula is defined. Okay, so I'm going to give you an example. Sketch the graph of the three common piecewise functions below. Okay, this is one of the piecewise functions that we are going to be focusing on. It's the absolute value function. Okay, so we can actually put f at x equals, and then this right here, remember from 1.2, the two sidebars that are straight, this means the absolute value function x. So the absolute value function x is actually a piecewise function. There's two different formulas that this breaks down into. Okay, it breaks down into x on the domain that x is greater than 0. So, for example, greater than 0, we're going to go up to the right where x equals y. Okay, and then we have negative x if x is less than 0. So anything less than 0, we're going to go up to the left. Okay, and these two lines, which we have, this is the line f at x equals x, and this is the line f at x equals negative x. These two lines make up the absolute value function. Okay, the ceiling function, which is x, and we have the brackets that almost look like it's putting a ceiling over x, right? These little parts here. Just make note of that it's not an absolute value function. Okay, where the ceiling function is the least integer greater than or equal to x. Okay, we're going to sketch this on the interval -4 to 4. So we're going to sketch it from here to here. That's our domain. Okay, so at -4, -3, we are not graphing, but all the way up to -3, -3, we're going to graph that. Okay, at -3, -2, we're not going to graph this, but we're going up. So if you think, oh, I put that on the wrong one. -4, -3. Sorry, ceiling. Okay, -2, draw it over to -1. So for this one, like -1, -1 is bubbled in. -2, -2 is bubbled in. -3, -3 is bubbled in. I'm also going to have to bubble in -4, -4. Okay, even though it's not defined that way, so I'm not going to actually put a line on that, but -4, -4 exists. Okay, and I'm just going to keep doing that. If you think of the word ceiling, you're thinking like the upper, right? So if I'm going from, for example, 2 to 3, I'm going to always draw in the upper one, like the ceiling, the upper. Okay, and then likewise for the floor function, if we take a look at these brackets are almost making a floor on the x, okay, where the floor function is the greatest integer less than or equal to x. So again, let's graph this on -4 to 4, and how we do that is we actually graph this time -4, 4, and we go to the right and we draw it open. So it's almost like, think of it like open at like the right as in like the ceiling and then closed on the floor. Okay, so at -3, 3, we bubble it in, but then it's open on the other end. -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3, and then I'm going to bubble in 4, 4, and then we're done. Evaluating piecewise functions. So to evaluate a piecewise function, determine which subfunction is used based on the domain restrictions given, and then substitute the independent variable into that piece and evaluate. So I have A, B, C, D, 4 different questions for one single piecewise function. So think of f at x equals, so it equals this absolute value function on x is less than 1. Remember, this is the absolute value function reflected in the x-axis, vertical stretch by a factor of 2 and left 1 unit, okay? Now we have a horizontal line, so this, don't be thrown off, f at x equals 2 is just a horizontal line through y equals 2. Obviously, f at x is another way of saying y, so it's y equals 2. And that's going to happen between 1 and 3. Okay, and then we have 5 minus 1/2 x. This is just a line with slope -1/2 and y-intercept 5. Okay, and that's going to occur on x is greater than or equal to 3. Okay, so a couple things. You have to really take a look at the inequalities, whether it's like underlined here, if it includes or doesn't include. Okay, so let's locate where in the domain is f at 12. Okay, f at 12 is in this part of the domain. So we're going to use, because 12 is greater than or equal to 3. So we're going to use, let's go, f at x equals 5 minus 1/2 x. And now we just sub it in. Okay, so I get 5 minus, what's -1/2 times 12? I get 6, so I get -1. Okay, now B, f at -5. Let's take a look at what part of the domain -5 lies. -5 is less than 1. So we're going to be using the absolute value function, -2 absolute value of x plus 1. So let's go ahead and plug in the -5. -5 plus 1 is -4. And then we can say the absolute value of -4 is +4. So overall, we get -8. Okay, f at 2. So take a look at these parts of the domain. 2 is greater than 1. So we're going to use, 2 is between 1 and 3. So we're going to use f at x equals 2. So f at 2 equals 2. That's it. Okay, there's no x variable there, so we're not subbing anything in. It's just horizontal line, y equals 2. Done. Okay, now last one, f at 3. This one's a little tricky. You have to really pay attention to the inequalities. Okay, so we have a 3 here and we have a 3 here. Which one of these equations includes the 3? So you're looking for the inequality with that underline. So it's definitely f at x equals 5 minus 1/2 x. And then all we have to do is sub in that 3. So we get 5 minus 3/2. So we get 3.5. Okay, so we just completed this question. Now what I want to do is actually graph this, okay? So we're just going to say graph f at x equals this piecewise function. So what we want to do is we want to have a graph here, and we're going to say, okay, here are like the 3 chunks of the domain that we're going to really take into account, okay? We're going to take into account when x equals 1 and below it. We're going to take into account between 1 and 3, and then 3 and above. Okay, so I'm just going to, and this is a sketch. So maybe I shouldn't say graph, maybe I should say sketch. Okay, so this is an absolute value function. So f at x equals -2 x plus 1. You always want to plug in this endpoint. So even though this endpoint is not actually going to be defined on this part of the graph, what we want to do is we want to consider this endpoint and then use it as like an open circle. Okay, so f at 1 equals -2, 1 plus 1, which is -2 times 2, which is -4. So at 1, we're going to graph an open circle at -4. Now, it's your choice. You could plug in f at 0, f at -1, and pretty much f at -2, if that makes you comfortable. I'm going to take a look at to see if this is an easy one to graph. So this is the graph of the absolute value function with the transformation left 1 unit. But you know what? There's a reflection and there's a stretch. So you know what? I am going to go ahead and plug in these numbers. So if you plug in 0 here, we get -2. If you plug in -1 plus 1, we get 0. And in -2 plus 1, we get -1, which is 1, and we get -2 again. So I'm going to go ahead and graph these points. 0, -2, -1, 0, and -2, -2. -1, 0, oops, and then -2, -2. Okay, and that makes sense. So I'm going to draw into the open circle, but not draw through it. And then I'm going to draw this, and this goes on forever. So put an arrow at the end. The reason why this makes sense is because if we compare this to what a quadratic would have as like the vertex, this vertex, quote unquote vertex, would be -1, 0. Well, -1, 0, we graph that, and that would be like that turnaround point. Okay, now let's do the next part in blue. So we have, and I'll put it up here, we have f at x equals 2, and then we have the domain including 1 all the way to 3, but not including 3. Okay, so we have the coordinates 1, 2 and 3, 2. No matter what, so f at x, we know another way of writing f at x is y, and we know when we have a horizontal line, all of the y's are going to equal that number. So let's graph 1, let's put a 2 here, that's fine. And we're going to fill that in. And we're going to graph this horizontally until 3. But the domain does not include 3 because it does not have this underline here in the inequality. So that's it for that one. All right, last part of this, we have a line, and it's going to be from 3, including 3, and then increasing. So I'm going to write f at x equals -5 minus 1/2 x. Now, you always want to sub in that those endpoints. So let's sub in a 3. So we have 5 minus 3/2, and I get 3.5. Okay, so this coordinate is going to be 3, 3.5. Let's just put it here. That's fine. And no, you don't have to put 3. You just put 3.5. It's totally fine. Now, here's the thing. You can go, like you can, if you want, sub in f at 4, f at 5, f at 6 for a couple points. I'm going to take a look at this, and I'm actually going to analyze what would this look like. So we have f at x equals, it's 5 minus 1/2 x. I'm going to switch these around to 1/2 x plus 5. Now, this is the slope, and this is the y-intercept. So, of course, the y-intercept would be here if it kept going up, which it doesn't. So I'll just do like a dotted line, so it's imaginary. But the slope is negative. So I'm just going to draw a line like this, and that's it. I'm going to call it a day. This is the graph of f at x. Okay, write the piecewise function that represents the graph. Okay, so for the first graph here, let's set this up. So we're going to do f at x equals, and this has 3 chunks of the piecewise function. So let's leave a little bit of space and like put a comma if, and let's talk about the domain that they're on first, okay? So for this first portion, it's on x is less than 2, and it's an open circle, so it's going to be just less than 2. Okay, the second one is on 2 to 5. 5 is open, 2 is filled in. So it's on 2 and includes 2, and then 5 but doesn't include 5. Okay, and then the third one, again, aligns. So that's so beautiful, it's so easy, and it goes from 5 to infinity. So x is greater than or equal to 5. Okay, so that is an easy part of this. Now we have to come up with equations for these 3 sections. So let's take a look at the first one. Okay, this is a line. I'm going to just do like a rise over run. So rise is -1, runs 2. Okay, so we know that that's going to be the slope, -1 over 2x. Now, what is the y-intercept? 5. So it's going to be plus 5. And for the second part here, we have a horizontal line at 3. So that's just f at x equals 3. Okay, and for this third portion, let's do the slope first. So -1 over 1, right? Because it's going down, it's going to have a negative slope. Now, this one is harder because we can't really see the y-intercept, but we can extend this, and then we see it's 7. So -x plus 7. Okay, and then this is the entire piecewise function. Okay, let's do b now. So let's call this f at x as well, or let's call it g at x. Okay, and we know that we have 3 segments in here. So we have from 2 and below. Okay, so if x is less than 2 or equal to, because this point is circled in, we have from 2 to 5, and that it does not include 2 and does not include 5, so no underlines in the inequalities there. And then we have if x is greater than or equal to 5. Okay, so let's go ahead and take a look at this first chunk. This is a parabola, so we know it's going to be an x squared. Okay, and we know it's going to be x squared because the vertex here is 0, -3. So if there was a shift left, right, we would have to put it inside the bracket with the x, but there's not, so it's just going to be x squared, and it's going to have a movement of down 3. So -3. And I can tell, but for the scope of this course, I'm not going to do any stretches here, so it's just x squared -3, and we're going to leave it like that. Okay, there's no stretch on this. And it doesn't open down, so it's not negative. That's it. Now, we have a horizontal line at -2, so that's done between 2 and 5. Okay, and the third portion of this, let's take a look at the slope. We go up 2 over 2. Oh, I guess up 1 over 1. So the slope is 1, so we have 1x. And then let's actually locate where the intercept would be, and it would be at -3 if we followed it all the way over. So x -3.